Hello and welcome you all for today's lecture on the subject thermal engineering, and today we are going to see the important questions from Msbte paper part 2. I am Mr. S.S. Sajni from Department of Mechanical Engineering, Sharad Institute of Technology Polytechnic, and I am teaching the subject thermal engineering. As already we have seen part 1 of this lecture, now we will continue with the second part, and today we will see all the questions from Msbte paper summer 19 and winter 18 respectively. So now let's start with the question. The first question is from summer 19 paper, and this question is asked for 4 marks. So we are having the question here as follows: define isentropic process and plot it on PV and TS diagram. So again we are having a theoretical question for 4 mark. So first we have to write the definition for isentropic process, which is nothing but the process in which working substance neither receives nor rejects heat to the surrounding during expansion or compression. So we call it as isentropic process, and for this definition you will be getting 2 marks. It is also necessary that you are writing the formula also for the isentropic process along with the definition, and after this you have to draw this isentropic process on PV and TS diagram. So you can see this representation of isentropic process on PV and TS diagram, and for drawing these 2 diagrams you will be getting 2 marks. So in this way the distribution is 2 plus 2 and a total of 4 marks. So you can see that in almost every paper such type of question is asked, that is define some of the process and represent it on PV and TS diagram. So you should know from all these questions that such type of question might be asked in the future paper also, and thus it is important part from second chapter. Now the next question from the paper summer 19, and we are having your question: a gas occupying 0.26 meter cube at 300 degrees Celsius and 0.4 megapascal pressure expands till volume becomes 0.441 meter cube and pressure 0.26 megapascal. So calculate the change in internal energy per kg of mass, and again they have given the values of specific heat at constant pressure and specific heat at constant volume, that is Cp is equal to 1 kilojoule per kg Kelvin, and this is actually Cv, which is equal to 0.71 kilojoule per kg Kelvin. So this question is asked for 4 marks, and I think we have already seen this question in our previous lecture. So we will just take a quick review of this question. So we have noted down all the given data, that is initial volume V1 is equal to 0.26 meter cube, then again initial pressure P1, it is equal to 0.4 megapascal, and you should remember what is the meaning of this megapascal, as we have already discussed this earlier. So megapascal is nothing but multiplication factor of 10 raised to 6, and 1 pascal is nothing but 1 Newton per meter square. So again we are having initial temperature as 300 degrees Celsius, so after converting it into Kelvin we will be getting 573 Kelvin. Then again final volume they have given equal to 0.441 meter cube, and the final pressure as 0.26 megapascal. So we have to calculate the final temperature T2, so that we can calculate the change in internal energy per kg of mass. So for calculating T2 we can use the formula, that is equation of state. So from this equation, that is P1 V1 by T1 equal to P2 V2 by T2, we can calculate the final temperature, that is T2. So after calculation you will be getting this value equal to 631.73 Kelvin. And once we get the value of T2, we can calculate the change in internal energy. Since they have asked per kg of mass, we are going to substitute mass equal to 1 kg. So by using this formula, that is mCv delta T, we can calculate this change in internal energy, which is equal to about 41.70 kilojoule per kg. So you will be getting 2 marks if you are able to calculate the value of T2, and the remaining 2 marks for calculating the change in internal energy. Again, the next question we are having here numerical, which is asked in the paper summer 19 for 4 marks, and the question is as follows. A gas has a volume of 0.14 meter cube and pressure 1.6 bar and a temperature 110 degrees Celsius. If the gas is compressed at constant pressure until its volume becomes 0.112 meter cube, then determine first work done in compression of gas and second heat given out by the gas. Now let's see how to solve this question. So first we have noted down the given data. So we have volume V1 equal to 0.14 meter cube, and since in the question they have given that the whole process is carried out at constant pressure, so it means that this process is an isobaric process, and thus we can take P1 equal to P2 is equal to 1.6 bar. So this pressure is converted into SI unit, that is 1.6 into 10 raised to 5 Newton per meter square. Then again we are having T1 temperature, which is given in degrees Celsius. So again we are converting this temperature into its SI unit. So in 110 we will be adding 273. So this will give up the value as 383 Kelvin. And after this again the volume, that is V2, is also given, which is equal to 0.112 meter cube. So we can just draw the diagram as we have already studied regarding the isobaric process and its representation on PVTS diagram. So you can see these diagrams as shown here. This numerical is very easy if and only if you are knowing what formulas are to be used for isobaric process. For solving this numerical, we just require 2 formulas, that is for work done and heat given out by the gas, that is nothing but heat transfer. And if you know the formulae, then just after looking at the given data, you will understand that you can easily calculate the work done because all the values are already available. Now if we want to calculate the heat transfer for isobaric process, then it is necessary to determine the T2 temperature. So first of all we will calculate the value of T2. Then for calculation of this temperature, we will be using the equation of state. So by this equation of state, we know that the ratio of P1 V1 to T1 is equal to P2 V2 by T2. So in this equation we are having all the values except the temperature T2. So we can easily calculate now T2. After substituting the given data in this formula, we will get the value of T2 as 306.4 Kelvin. Now let's see the calculation part of work done and heat transfer. So work done in compression of gas, we can calculate this by formula, that is dW is equal to P into delta V, that is P into V2 minus V1. So the pressure they have given, which is 1.5 into 10 raised to 5 Newton per meter square, and V2 volume we are having as 0.112, and V1 we will be subtracting from this value, that is minus 0.14. So the value of work done we will get directly, and it will be equal to minus 4480 joule. So again we can convert this into kilojoule. So in terms of kilojoule, this answer will be equal to minus 4.48 kilojoule. Now for the calculation of heat transfer, we will be using this formula, that is dq is equal to du plus dw, or again we are having another formula, that is mCp into delta T. We can also calculate the heat transfer by using this formula. Since they have not given any mass related information in the question, so we can assume this mass equal to be 1, and also we are not having the value of Cp, that is specific heat at constant pressure, so we are usually considering this value equal to 1. So after substituting these values, that is 1 into 1, and T2 we have calculated, which is equal to 306.4, and subtracting the T1 temperature from this value, that is minus 383. So finally we will be getting the answer as minus 76.6 kilojoule. So this is the heat transfer. And if you look at the mark distribution, then for calculation of work done, you will be getting 1 mark. For heat transfer, you will get 1 mark. And earlier we have calculated the value of T2, so for that purpose you might get 1 mark. And for conversion process or representing the process on PVTS diagram, you will be getting 1 mark. So in this way, the 4 marks question, it is distributed in this way. Now let's see the next question from the same paper. Again we are having here numerical, which is asked for 4 marks in the same paper, and the question is as follows. A certain gas has a specific heat at constant pressure equal to 1.968 kilojoule per kg Kelvin, and Cv, that is specific heat at constant volume, equal to 1.507 kilojoule per kg Kelvin. Find the molecular weight and the gas constant. A constant volume chamber of 0.3 meter cube capacity contains 2 kg of this gas at 5 degrees Celsius. Heat is transferred to the gas until the temperature is 100 degrees Celsius. Find the work done and change in internal energy. So now let's see the solution for this question also. So first of all, we will note down as usual the given data. We have given the values of Cp and Cv, that is equal to 1.968 and 1.507 kilojoule per kg Kelvin. Again they have given constant volume, so this process is called as Isochoric process, and we are having volume as 0.3 meter cube. Again mass they have given as 2 kg. Again we are having T1 temperature equal to 5 degrees Celsius. So after converting it into Kelvin, we will get this value as 278 Kelvin. And the T2 temperature is 100 degrees Celsius. So after converting it into its SI unit, we will get value as 373 Kelvin. Now in this question, they have asked us to calculate 4 parameters, that is the molecular weight, gas constant, work done, and change in internal energy for this isochoric process. So first we will see how to calculate the molecular weight and the gas constant. So for this purpose, we should know that the gas constant, that is R, it is calculated by taking the difference of specific heat, that is Cp minus Cv. So you should remember this formula, that is R is equal to Cp minus Cv, and you will directly get the answer or the value of R, that is 0.461 kilojoule per kg Kelvin. So we have obtained the value of gas constant. Now to determine the value of molecular weight, we will use the formula which we have studied in relation with universal gas constant and characteristic gas constant. We know that the universal gas constant, it is the product of characteristic gas constant and molecular weight. So by using this formula, we can calculate the value of molecular weight. As already we know that the value of universal gas constant, it is equal to 8.314. So by substituting this value as well as the value of gas constant which we have just calculated, after substituting both these values of gas constant we will get the molecular weight equal to 18 kg. Okay, so this is a simple formula, that is m is equal to the ratio of universal gas constant to characteristic gas constant, and this will give us answer equal to 18 kg. Now we'll find out the remaining two parameters, that is work done and internal energy. So here this question is very tricky one, because you should know that they have given volume as constant, that is for isochoric process work done is always 0, and hence there is no need of any formula for calculating the work done. So the answer will be directly equal to 0, that is work done for isochoric process, it is always equal to 0. Now if we look at the remaining part, that is change in internal energy, then we can determine this value by using the first law of thermodynamics, which is given as heat transfer is equal to change in internal energy plus work. However, we have determined that work is equal to 0. So if we substitute this value of work in this equation, that is in first law of thermodynamics, then we will be getting as heat transfer equal to change in internal energy. And as we know how to calculate the heat transfer, that is by using formula Q is equal to mCV delta T. We will first calculate the heat transfer. We have to just substitute the value of mass equal to 2. CV they have given in the question, that is 1.507, and both temperatures we are already having. So after substituting this value, we will get heat transfer equal to 286.33 kilojoule per kg. And now as per the first law of thermodynamics, we know that this heat transfer is equal to change in internal energy. So directly we can write the value of change in internal energy, which will be equal to 286.33 kilojoule per kg. So this question is for 4 marks and you will be getting 1 mark for calculating all of these 4 parameters that they have asked in the question. That is 1 mark for molecular weight, 1 mark for gas constant, 1 mark for calculating the work done, and 1 mark for determining the change in internal energy. I hope that you have now understood this numerical. Now let's see the next question. So we are having your theoretical question with a great weightage, that is this question has been asked for 6 marks, and the question is derived characteristic gas equation using Boyle's law and Charles' law. So again we have already studied this point. We have derived the equation that is equation of state, and from this same equation we can also derive the characteristic gas equation. So just one more step we will be having here extra, otherwise the rest of the part is same. After looking at this slide, I think you might remember all those points which we have studied, what steps are there for deriving this equation. So we have considered 2 processes, that is constant pressure process and constant temperature process, and after applying Charles' law and Boyle's law, we have determined the values of VA, which is the common point for both this process. So after substituting the right hand side of the determined values of VA, we have obtained the equation which is called as equation of state, and this equation is nothing but the ratio of PV by T is equal to constant. But since they have asked in the question to derive the characteristic gas equation, so one more step we have to add here. Just we can replace, instead of writing constant on the right hand side, we will take the denominator of left hand side, that is temperature, to the right hand side, and the constant we will be representing it as capital R, which is characteristic gas constant. And again, if we are considering m kg of gas, then we have to multiply the right hand side by m kg. So the final characteristic gas equation will be PV is equal to mRT, and for deriving up to this step you will be getting 6 marks. So this was all about the important questions. or the questions which were asked in the Msbt paper, that is from summer 19 paper, and a total of 22 marks weightage was given in this paper for this second chapter, that is ideal gas and ideal gas process. Out of this 22, you can see that 10 marks were theoretical based questions, whereas the rest of 12 marks are numerical based. So if you are just concentrating on the theoretical points, then you will be not able to score maximum marks for this chapter. So I would like to suggest you to focus more on numericals for this particular chapter. With this, we will stop here now today, and we will see the last paper, that is important questions from winter 18 Msbt paper, in the next lecture. Till then, thank you very much.